Good morning, everyone. So today we'll just I was thinking we'll directly jump to the questions because that's pretty much what the sessions are for. But before that, we'll just talk about the areas that was covered in this week's lectures. Predominantly, this week was about something called content distribution networks or CDNs, right? And then it's also about something called information-centric networking. So these are the two main topics which was covered this week. And I think the questions are broad enough for us to understand this through the questions themselves. Right, so let's get on to the questions. Get on to the questions. Right. So which of the following naming convention in information-centric networking is structured similar to the current uniform resource locators and allows the creation of user-friendly and meaningful names? So basically INC, right? So INC, you can look at this like an alternative model for the internet. Right? So right now internet exists in a particular way where we look at some resources. We look up some resources using URLs, right? So INC is a different method to envision the internet, right? Information centric networking, right? The resources become the backbone of the internet. It's very clearly explained in the videos of this week. So which of the following naming conventions is structured similar to the current URLs? So what are URLs? URLs are something like HTTPS as to something.com, right? So this is a way in which we define a resource, uniform resource locator. Right? So it's hierarchical. First the protocol, and then the which domain is it? Is it World Wide Web? And then the specific name, and then there is .com or something else. Right? It's a hierarchical way. So similarly, the concept of INC also proposed something which is hierarchical, right? And what are they called as? The answer is B, hierarchical names. So basically, what happens is in information centric networking, the network shifts its focus. I think I'm slightly following a different method from this week. So I'm going to write down some amount of background for each question so that um, it probably will be helpful. So in INC, the network, its focus from addressing hosts, which are basically machines, to addressing the data or the content itself. So as a result, the names that represent content need to be easily understood and routable. So when you route based on a resource, that's the concept of INC. So when it comes to hierarchical names, right? So the answer here is hierarchical names. Hierarchical names so they are organized in a tree-like structure. So something like slash university slash CS slash lecture one. So this is very similar to something like this, right? So URLs, they follow something like domain, subdomain, and resource format, right? So what we have to see is this structure also, it allows for names to be easily remembered, manage, and map content. So this is pretty much what you have to understand about INC. And why not the other options? So if you look at flat names, so these flat names, they are basically typically random names or hash based names, which possibly could not offer any readable or descriptive components, right? This is flat name, so this is doesn't make sense. It can be anything. You pretty much you can just type in anything and that becomes a name. There's no structure, there's no organized structure. So you can't route based on those names. So attribute value based names. And although they use metadata, they do not naturally create a structured path that hierarchical name uses. Again, there's no structured path because something like university CS lecture 1, lecture 2, lecture 3. So you can just keep changing the last part of it and then you can keep moving on. So this creates some logical structure. But if you can't create this logical structure, then every resource is floating on the internet as individual entities. So it becomes difficult to club them together or understand the relationship between these different lectures if they are just stored as lecture 1, lecture 2, lecture 3, something like that. Right? So this is also not going to help the case. And finally, dynamic names. This pretty much means that the names will change based on context or um, over time, which probably could lead to difficulties in naming consistency and probably routing as well. Right? So things that change. Dynamic is stuff that changes. So the first one's answer is hierarchical names. And I'm going a bit slow, uh, but I think it'll probably speed up in a few questions. So in traditional IP internet, what is the state of the routing and forwarding plane? So in traditional IP internet, right? So there is a routing plane and there is a forwarding plane, right? So routing is typically the control aspect, and forwarding typically happens in the data plane. I hope we remember this much. So now there are some statements, and we'll have to choose which of these statements is correct. So yeah, again, it's not mentioned properly here, but that's what it's supposed to do here. So they're saying both are stateful and adaptive. They're saying routeful is stateful and adaptive while forwarding is stateless. Both are stateless and have no adaptability. Forwarding is stateful and adaptive while routing is stateless. So let's look at the first statement. Or rather, I think let's refresh about IP networking itself. So IP networking, this is traditional networking, is basically what we use right now. You have something called the routing plane, right? So what are all its functions? So it basically, let's say, it determines. So routing plane, you can call this to be the work of the uh, the control plane as well. Okay. So it determines the best path through the network. So to do that, it might use some routing protocols like OSPF or BGP. And also, once it uses that, it also maintains routing tables. And these, they change in response to network conditions. So, but when you look at the forwarding plane, right? So this is basically responsible for moving packets from the input interface to the correct output interface. According to the computed routing tables. Right, and who computed this? The routing plane. So in order to move packets from the input interface of the router, let's say, right? So there are this many input interfaces, this many output interfaces. It just takes the packet from here and puts it here, puts it here, puts it here, depending upon the routing table. So to do this, it does not need any state. Need to retain state. Okay. Right. So with this, we can try and answer that routing is stateful and adaptive while forwarding is stateless. So what state, generally what it means in the context of networking is you store some information about the previous process. So basically one packet comes and then you store something about it, and based on that state, you process the second packet. But here that happens only for routing, because routing needs a global view where it can probably find out the correct path, and for that it needs to maintain the state of the other routers or the other nodes in the network and generate its own topology. And based on that topology, which is also nothing but state is nothing but memory. Based on that memory, or what's there in this in the memory, which is basically the state of the network, it comes up with some path or route. Okay. So that is why routing is stateful and adaptive, while forwarding is stateless. Now, if we look at option A, both are stateful, it is not true. Option C is both are stateless and have no adaptability. No. Forwarding is stateful and adaptive, while routing is stateless is the converse of B. So the answer is B. And here the answer is B as well. Right. I'm just putting the answer separately. So which of the following is a popular ICN architecture? So information-centric networking, which of the following is an ICN architecture? So I think by looking at the options itself, you should be. I mean, probably it'll hit you that SDN is a separate architecture all by itself. So it doesn't make sense. And CDNs, they're there for a different purpose altogether. Multi-protocol label switching, MLS is also it's more about efficient packet forwarding, and which uses labeling and not about naming the content directly. So this is also not the answer. So of course, named data networking. This is what remained. So the answer is this. But what does this named data networking do? This is clearly explained in the videos, but I'll just summarize it down here. So communication NDN is driven by content retrieval net requests. Something called interest packets. Right. So this is interest packets are sent, and then in response to interest packets, we get back the corresponding data packets. Right. So NDN. This is pretty much small summary for it. Right. That question was pretty simple. So now they're asking, what is the main advantage of ICN over traditional IP-based networking? Right? Is it faster connection speeds? Is it easier network configuration? Is it more efficient content distribution, or is it lower power consumption? Okay. So what is the advantage of ICN over traditional IP-based networking? So let's look at ICN versus IP. IP is host-centric, which means that communication is established between specific endpoints. So in contrast to that, ICN is designed with a focus on the content itself. All right. So the advantage, right? So we're talking about the advantages of ICN. One of them is in-network caching. So as we saw, ICN architectures like NDN, they enable routers and other nodes to cache content. So which means that if one piece of a content is retrieved by a user, it will be stored or it may be stored in intermediary nodes, right? So content can be stored in intermediate nodes and delivered to subsequent users faster. So this is the advantage of this is the in-network caching advantage. And the second is we can say it reduces redundancy so because content requests can be satisfied from nearby caches, the network avoids repeatedly fetching the same data from a central server. So because like the same data is spread all across the internet here, um, the network is more efficient, avoids repeatedly fetching the same data from a central server. And probably the third one that we can say is lower latency. Is lower latency. So this is like caching. Because of the caching, which is closer to the user, it reduces transmission delays. Okay. Right. So again, now with this context, what is the main advantage of ICN over traditional IP-based networking? Um, is it faster connection speeds? Is it easier network configuration? Probably not. Right? Is it more efficient content distribution? Or is it lower power consumption? So A, B, and D are, I mean, all of them are somewhat true, somewhat similar. But what is the main advantage of ICN? If they're asking what is the main advantage, the main advantage is just C, more efficient content distribution. That's what this is. This kind of encompasses everything, more efficient, right? So this C tends to cover up A, B, and C in some ways. More A and D, but yeah. So this is the correct answer. So how does ICN handle? So how does ICN handle security differently compared to traditional IP networks? So now they're talking about the difference based on security, right? So does it rely on end-to-end encryption, or does it use firewall to protect against intrusions, or does it use VPNs to secure data transmission, or does it secure the content itself regardless of where it is in the network, right? So I mean, once you look at the videos of this week, you would know that the answer is D, right? It secures the content itself regardless of where it is in the network. So why? Because security in ICN, here security is embedded at the data level, right? So each content chunk carries cryptographic signatures that validate authenticity and integrity, independent of its path or the storage location. Okay, so basically this answer D, right? So this is nothing but content centric security. So this content centric security, what that means is regardless of where the data is cached or transmitted, the data itself is verifiable, making attacks such as content tampering much more difficult. right? So why not the other options? So if you look at option A, it relies on end-to-end encryption. So end-to-end encryption is basically protecting the channel itself, right? So this is happening in traditional IP-based networks. But in information-centric networking, they propose to protect the data itself, right? So this is not the answer. I mean, firewalls are usually used in IP networks, and these are perimeter protections. And of course, they can be used in ICNs, but they are not the primary method for securing content in ICNs, right? And see, VPNs. So this secures the communication channels rather than securing the individual data packet itself. This is also like another encryption layer, right? So that's why the answer is D. So the next question is about in-network caching in information-centric networking. See if you can answer this question. I'll be back in 2 minutes. So which of the following statements best describe in-network caching? Right. So I think we already looked at the concept of INC. So they basically are saying that content is stored only at the router to which the content consumer is directly connected, or ICN provides flexibility to cache content only at the intermediate routers located along the content delivery path. Right? Or ICN provides flexibility to cache content at any router in any shape or size of the network topology. Or ICN provides flexibility to cache content at any router in the uh, hierarchical tree uh, of the network topology, right? So if you look at all of these statements, this more becomes like which is the best fit for all of these? Which is the best fit for uh, the answer? Because not all of them are completely wrong also, right? Okay, so if we look at A, right, content is stored only in the router to which the content consumer is directly connected. So this is not what ICN is for, because it is too restrictive. It limits caching to the consumer's adjacent router, which is basically the router at your own house. When the content is not placed far well within the internet, so that other people can benefit from the same content, right? So A is not the answer. And B, ICN provides flexibility to cache content only at the intermediate routers located along the content delivery path. So here they are saying only at the intermediate routers. So this implies that caching is confined only to nodes along a predetermined delivery path, which is pretty much not the case in ICN. Right? So because of that, this is also wrong. And looking at option D, or sorry, option C, so ICN provides flexibility to cache content at any router in any shape or size of the network topology. So ideally, this is exactly what um, it was proposed. This is what was proposed. Ideally, this is what was proposed. Okay, so this looks correct. And finally, ICN provides flexibility to cache content at any router in the hierarchical tree or shape of the network topology. So here, trickily enough, this statement suggests that the network's shape is strictly hierarchical, right? Which is not the case in ICN. So because of that, you can eliminate this particular option. And what is left out is C, which is basically talking about content being in any part of the network, in any shape, way, or form, right? So what this also talks about is its flexibility and ubiquity. So ICN does not restrict caching to a particular topology, shape, or location. Right? So, and that's the flexibility and ubiquity component of ICNs. So again, caching is basically a cornerstone of ICN and is used to store copies of data at various points in the network. And this reduces the distance the data must travel and minimizes redundant transmissions. This is what we saw about in network. caching, right? So the answer here is C. So the named data networking, NDN, right? This is nothing but a specific architecture of ICNs, right? What happens in NDN? So here basically they're asking which of the following is transmitted by the NDN, right? Is it named data chunks? Is it IP chunks? Is it named movies? Or is it all three types? I think just looking at the answers itself, we can kind of like uh, come to a conclusion that it is not movies. It isn't, I mean, of course, it's not movies. And IP chunks is for IP based networking. And because these two are not the case, all three types are also not the answers. The answer is A. But let's look at the background. Correct. In NDN, data is segmented into chunks that are each given a unique name. All right. So because of this, in NDN, consumers issue interest packets that request data by name. The corresponding data packets contain the actual content. Each identified by a unique name. So this method differentiates it from traditional IP communications. right? So again, this is something that you could see in the video as well. So, but I thought if I write down the exact background for that particular question on the sheet, probably you can just go through it and you can just revise based on it. So that's pretty much why I've changed the strategy for this week. I'm just writing down the relevant information for that particular question, right? So the answer is A, which we have already seen. Now we are shifting back to information from ICNs. We are shifting back to CDNs, which is content delivery networks. Now these are very easy concepts to understand. CDNs compared to ICN, right? Because ICN was a completely different concept. With CDNs, uh, it's relatively easy to understand because they are actually used in this, I mean, the current IP networks, because most of your Netflix and streaming platforms, which pretty much have to stream the same data over and over again on the internet, place the content somewhere near a particular geolocation. Essentially, I don't want to go into the details. The videos talk about this better than I ever can. So, well, the question is, which of the following is a unique mechanism employed by CDNs to enhance a bandwidth efficiency by reducing the distance between the user and the server, right? And thereby reducing latency and improving site load times. So essentially, this is like the definition of CDN itself that they've given. But what is the mechanism that is used by CDNs to achieve this? Hmm? So, A, CDNs optimize bandwidth usage through dynamic compression algorithms, adapting to varying network conditions. Or is it B, CDNs improve bandwidth efficiency by implementing intelligent routing based on real-time traffic analysis? Or is it C, CDNs utilize advanced packet prioritization techniques, ensuring efficient use of available bandwidth? Or is it D, CDNs enhance bandwidth efficiency through efficient content distribution mechanisms such as caching and replication? So if you look at all of these options, the answer is D. So why not A? Compression definitely is a useful mechanism, but it is not the key mechanism for reducing the physical distance that the content must travel, right? So how do they reduce the distance? They reduce it through efficient caching and replication mechanisms, which is why A is not the answer. If you look at B, CDNs, they improve bandwidth efficiency by implementing intelligent routing based on real-time traffic analysis. So this is all high level, not high level, very complicated strategies, which even now we don't have truly intelligent routing. So, and especially CDNs don't do this. They just have to throw data at the user that is being requested for. So this is also not the answer. It definitely helps, but it does not directly tackle the issue of distance or redundancy, right? And C, although it is important, basically advanced packet prioritization techniques, it is important. Um, it is not the central mechanism for enhancing bandwidth efficiency in CDNs. It is not. Right. So the answer is D. I mean, it's a straightforward answer. So, which of the following techniques is slash are not commonly used for content delivery optimizations in the current IP-based networks? So, we're talking about the current IP-based networks, and which of them is not commonly used in this paradigm, current paradigm. Again, this is pretty straightforward. CDNs, they are definitely used in IP-based networks only, right? Transparent caching, transparent caching is basically when routers or gateways could cache content to reduce retrieval times. So this is also done in current IP-based networks. Flooding, it is not that commonly used. It is pretty much non-existent in IP-based networks. So this is the answer. And peer-to-peer systems. So peer-to-peer systems, they leverage distributed user content resources to share content, effectively optimizing delivery, right? So this is peer-to-peer, like torrents and stuff. They use peer-to-peer networks. This is also used in IP-based networks. So what is this flooding, right? Um, so this flooding is nothing but it's a it involves sending copies of data to every possible route until the destination is reached. So it involves over every possible route until the destination is reached. It is inefficient and scales poorly in large networks. And because imagine if you ask for a particular movie and then just to send that movie to you, that movie is sent like through all the routes available on the internet. So that's redundant, that's waste, right? So it's not used in this context of IP-based networking, right? So the answer is C. Which of the following statements is slash are false about IP and ICN, right? We're talking about both IP and ICN here. So it will mostly be comparative statements. Let's compare IP and ICN. So the address space of IP is larger than that of ICN? No. In ICN, the resources themselves can be used as the addresses, right? So which means the space for addresses is huge. But in IP, it is basically 2 to the power 32. That's what it is. So this statement is false. So ICN reduces the need for centralized servers for content storage. This is true because with in-network caching and a distributed content delivery, ICN naturally minimizes reliance on central servers. So this is true. Statement C is ICN focuses on a host-to-host communication paradigm. Right? So ICN emphasizes content retrieval by name rather than establishing a connection to a specific host. So it is not host to host again. So this is false. These are all very straightforward statements. So IP and ICN cannot coexist in the same network. This is false because, uh, as we've seen in the video, there are architectures, including overlay networks, that allow both IP-based and ICN-based communications to coexist. And so, in fact, many experimental and hybrid networks support both the paradigms, ICN as well as IP-based networks. In fact, I mean, as of now, ICN is not a well uh, structured, or rather, it's not actually used in a lot of places. I don't even know if it's actually being used in a proper production network, but it's a concept. It's a new way of looking at the internet, which has been researched upon, right? Um, so the answer here, A, C, and D. So, which of the following statements are incorrect about CDNs? A CDN comprises a single centralized server that caches its contents. CDN distributes the content to end users through a set of CDN servers. CDN prevents servers from becoming overloaded. CDN is deployed as an overlay network on top of the existing network to host the content close to the end users. Right? So just looking at it, you can basically say that A is false. Right? Why? Because it is not a single centralized server. It is not. It's called content delivery networks or distribution networks, you can say. Right? So it is separated across different geographical locations itself, if you look at it like that. So A, it is false, and B, CDN distributes the content to end users through a set of CDN servers. That's exactly what CDN does. So it is true. So CDN prevents servers from becoming overloaded. Also true. Why? Because you are not keeping only the central data only in the centralized location. You're distributed. So the load is distributed across multiple servers. or multiple locations. And CDN is deployed as an overlay network on top of existing networks to host the content close to the end user. This is also true. Right, so what? So this overlay network is basically nothing but it is a network on top of a network. It's a network on top of a network. And on top of which kind of a network? On top of an IP network. Right. So yeah. So the answer is A. So which of the following techniques are commonly used for content delivery optimizations in the current IP-based networks? Right. So it's very similar to the previous question. So, but they're asking here, there are some techniques that are used for content delivery uh, in the current IP-based networks. What are these techniques? So the techniques are content distribution networks, which is CDNs, right? And there's another thing called transparent caching, which is also another technique, right? IP unicasting is not used for this because unicasting means point to point, A to B. But multicasting is A to multiple places, one to many places, right? So this is one to many. Right. So it's pretty much of a no-brainer that the answer is A, B, and D. And D. Okay. But let's kind of take a look at what the individual um, techniques are. I'll just speak about it. I won't write about it because I think we've written enough context in the very first set of questions. So, A, content distribution networks. That's pretty much what the whole videos were about this week. So, as explained above, um, CDNs are essential for distributing content across multiple servers to reduce latency and avoid congestion. And they form the backbone for rapid content delivery. So what was transparent caching, which is option B? So transparent caching is done when intermediate nodes like proxy servers or routers themselves are used to store copies of frequently requested content. So we can usually see this in the context of um, uh, DNS servers, right? So you tend to cache the IP address of certain domain names. So either way, when a request is made, the cached copy can be served instead of fetching the data from the original server, leading to faster response times and reduced network load. So this is B. But here we are storing bigger data, right? And IP unicasting. So IP unicasting is a standard method for point-to-point communication, right? So the one-to-one, point-to-point. But just a minute. So it is the um, used for point-to-point communication, but does not optimize delivery when the same content is needed by multiple users. So one-to-one is pretty much not going to help you here. And multicasting is the opposite of, or rather the better version of unicasting. Uni multi, right? So the technique allows simultaneous transmission of data to a group of hosts, to a group of people. And this reduces redundancy in the data, which is being sent over the network when many users request the same content. Right? So this is why the answers are A, B, and D. Which of the following is not true about the information-centric networking? So this is something that's directly from the um, videos themselves, right? So if we look at this, efficient content distribution. So this is ICN's cornerstone. So this is not the answer. Ubiquitous caching. We saw this also previously. I had written down ubiquitous caching also at one point. And see, data is dependent on the application. No. Data is dependent on the location. Absolutely not. Name-based routing. Yes. So in the context of this, it is C and D. So because we spend some time, we're able to pretty much answer these questions. So basically, if you want to get the details about why these two are incorrect, see, when it comes to option C, data is identified by names rather than being tied to a specific application that generated it. So the focus is on the data's content, not the context in which it was created. And secondly, option D. So data in ICN is decoupled from the location. So with name-based routing and caching, data can be retrieved from anywhere in the network, which wherever the copy is held, right? It's not necessarily from a fixed location. Okay, so answer is C and D. Which of the following is a major challenge in deploying ICN? Is it a difficulty in securing and protecting data? Is it the difficulty in caching the data? Or is it the incompatibility with legacy IP based systems? Or is it the inefficiency in terms of routing the requests? So, while all of these are challenges at one level, at some level, the most major challenge here, right, is incompatibility with legacy IP based systems. Right? Uh, and why is that? It is so because the internet infrastructure, as I'll write this down, the internet, so the answer is C. The internet infrastructure is largely built on IP addressing and host centric routing. So if we have to replace, right, using ICN is a substantial technical and operational hurdle. Right? And that's pretty much why this is the answer. Now, yeah, it is actually time, but um, I mean, you guys are free to leave, but I'll finish off the rest of the questions and you can watch it in recording later as well. So it's okay to stay back and it's okay for you to leave as well. It's completely fine. All right. So question number 5 is which of the following statements? And which of the following statements is or are incorrect about traditional IP-based content caching techniques? So A, transparent caching schemes do not improve the response time. Um, Transparent caching is basically when you cache data onto intermediate, let's say routers or um, proxy servers or anything in the middle, right? So this actually improves the response time because you're caching. So this is the statement is wrong. So which means it is correct as far as this particular question is concerned. So transparent caching schemes are usually managed by service providers. Um, it is correct because the service providers are big enough to have equipment which can cache and they have the right incentive to optimize network bandwidth as well. So this is correct, which means it's wrong in the context of this question. So transparent caching schemes can intelligently decide which content can be cached locally. right? So this is also correct because based on if a particular content is becoming hotter, when I say hot, it means it is being requested more than a particular amount of time, right? So these are all mostly requested contents. So only those content is cached. This is also a correct statement. So in web caching, if two copies of content C are stored on the servers belonging to different providers, the caching system will access the content using the same URL. So in web caching, if identical content exists on different servers, the URLs will differ. So even if the content is the same, the identification used by caching systems is URL specific. So because of that, the system will not necessarily use the same URL to access two copies. So basically, it's not named data networking where one content that is the same uh, is the same all across. So the same copy, even if it is there in multiple servers, you will have to access it using different addresses because its house is in different places. All right. So this is also wrong. So the answers are A and D. Right. What is the role of forwarding information base in ICN? Right. So FIB is also a concept in IP-based networking, but in IP-based networking, FIB stores the next hop. Correct. It is basically a routing table in which you have the it's a distillation from the routing table, which in which it's basically said what which port you're supposed to forward the packet onto, and in the bigger context, which route it's supposed to take. But so what is the role of this forwarding information base in ICN? Is it A to store content objects? Is it B to store addresses? Is it C to store outgoing interfaces per each known named prefix, or is it D to track the forwarded requests? So in the context of ICN, the FIB is a data structure that maps content name prefixes to the appropriate outgoing interfaces. It's very similar to IP-based networking, but what is being mapped? Content name prefixes to appropriate outgoing interfaces. Right. So this allows routers to know through which interface to forward a request for a particular content name. Right. So this is pretty much about, I think, FIB and ICN. I think, yeah, this is enough context. Um, so again, this is not the case, this is not the case, this is not the case. So the answer is C. So what are the major challenges associated with multi-point distribution in the current internet architecture? So what is the multi-point distribution? Right? This multi-point distribution, so this is something like IP multicast. is good for efficient content delivery, but the need to manage state information and ensure security and support mobile users are notable hurdles. Right. So again, I think I've just written basically what so these three are the challenges associated with it. So the answers are A, B, and C. A, comma, B, comma, C. And network congestion, it reduces network congestion to be honest. Right. So um, okay. So how does an ICN handle requests for content? Meaning it's just how it works. How does ICN work? Right. So it routes request to a specific server based on requester's IP address. No, this is basically IP based routing. So is it using a content name to locate and retrieve data from any available network node? Yes, this is true. By broadcasting the request to all devices on the network? No. Right, this is very straightforward. And by sending the request to a specific server based on the content's location. Mm, probably not. I mean, it's definitely not, sorry. So the answer is B. So it is using a content name to locate and retrieve data from any available network node. That's pretty much what ICN does, right? Named data networking. Correct. So yeah, that's pretty much about 8. So let's go to 9. Consider the table below to match the ICN content naming scheme to their correct representational structure. So I think this is something that's, I mean, if you see the video, you can easily understand. But uh, the answer, let's take a look, right? So flat. So flat means you just write the name of the content directly, just like that, as it is. So and that will use something like a hash function. I spoke about this in the beginning, right? So P goes to 2, right? Hierarchical. Hierarchical would mean you will have a hierarchy in it. So where do you see hierarchy? Is it 1 or 3? It is basically 3, right? So Q is 3 and R is one. That's the only one left out basically, right? So, but again, that is attribute based. The attribute of the content defines the content itself. Right? So the answer here is C. So the final question for today is, which of the following statements is slash are incorrect about the security model of the current TCP slash IP network and information centric networking? So TCP IP protects the communication channel between a client and a server using TLS. This is true. It does. ICN protects the communication channel between a client and a server. Um, no, it doesn't specify anything directly of that in those wordings or in those terms. It basically just, it does not rely on securing the communication channel, but instead its security model is built into the data itself. It ensures that the content is authentic and has not been tampered with, regardless of its transmission path. Right. So this is false. IC networks use data encryption authentication mechanisms at the transport layer. So it is also wrong because TCP/IP adds security at the transport layer, but ICN applies cryptographic security mechanisms directly to the data packets. Which it means that each packet is either signed or encrypted at the data level. It does not depend on conventional transport layer encryption for content authenticity or integrity. So again, this transport layer is a dead giveaway here because when we say transport layer, we talk about IP networks. This is false. Option D, in ICN, packet content and names are associated with strong cryptographic primitives. So yes, in ICN, strong cryptographic mechanisms are associated with both the content and its name. So this ensures that data is data. I mean, they kind of ensures data integrity and authenticity, right? Right. So this is true. So they're talking about incorrect answers, right? So which means the answers are B and C. And this puts a close over today's session. I think a slightly different strategy was followed this session. I kind of wrote down a lot of things. Um, so if you have any questions, you can ask me. If not, you're free to leave. And yeah, right. Right. All right. So you're free to leave. Right. Thank you.